Welcome, my name is Johnny Bandon, and I'm going to be your CCNA instructor for this CCNA video series. And now we're going to jump into OSPF. So hopefully you just watched our intro video, a lot of good information in there about how to further learn OSPF. Let's go ahead and jump right into it. Okay, so OSPF Overview. So OSPF stands for the Open Shortest Path First Protocol. It is going to be a vendor-neutral, dynamic, link state routing protocol. All that to say that you can run OSPF on any vendor that's going to support it, right? It's open source, essentially. Anyone can run OSPF if they decide to build a router or a routing device. It is a dynamic routing protocol, so different than static, obviously. And then it's a link state routing protocol, which means a lot of things, right? We went over this in the intro to IP routing, but essentially a link state routing protocol, a couple keynotes. It's a fully converged network, and every device within a routing area is going to have the same link state database. A link state routing protocol also relies heavily on, you guessed it, the state of a link, right? Crazy. But that link's bandwidth, what type of network that link is, affects how OSPF chooses best paths and how it operates. So really this link state routing protocol all depends on the physical interfaces or the logical ones coming out of your router or routing device. So a couple features of OSPF. One, it's efficient. It has fast convergence on the network. It is scalable, especially within your enterprises and your autonomous systems. And it can also be secure. It does support authentication in its hello packets, like a lot of routing protocols do nowadays, and it does do MD5. Some other things that aren't on here, we're at OSPF version 2. That's for IPv4, OSPF v2, and then OSPF v3 is for IPv6, which will be covered in our IPv6 section. Okay, more overview. So now we're just going to go over a high-level overview of how OSPF works and functions just with these blurbs, right? So what's going to happen when two routers want to run OSPF and discover each other using OSPF and become neighbors? Any OSPF-enabled interface is going to send what we call an OSPF hello packet to its neighbor. And depending on the network type, whether, broadcast network, it's going to send out a multicast as the destination IP, and any OSPF-enabled interface should be listening to that multicast address. And in that hello packet, there exist parameters. These parameters will have to match according to OSPF, right? And then if those parameters match, then those OSPF-enabled interfaces will become neighbors, essentially making these routers neighbors, right? And I keep saying interfaces or links when referring to OSPF, because remember what type of routing protocol it is. It's a link state routing protocol. So you're going to hear that language a lot when I describe OSPF. Because I know when I first started learning, and it's okay, but a lot of trainers and even in industry, we say, oh, that OSPF router. Now, no one's going to be like, well, actually, that's an OSPF-enabled link that runs OSPF. That router runs OSPF, right? No one's going to do that. But for the exam purposes, I'm going to try to hone that concept in that this link has OSPF enabled on it, right? So what's required to match for OSPF-enabled interfaces to become neighbors? So you're going to need your hello and hold timers to match. And there are default timers on these, 10 and 40, and then 30 and 120, excuse me. Again, depending on the type of network. Let's put NT for network type. On whether or not it's going to be 10 and 40 or 30 and 120. And for anybody that, loves math, you're going to notice something, that this hello timer is just times 4, or this hold timer is times 4 of this hello timer. So what does that mean, right? Essentially, it's supposed to mean that if you change the hello timer to 5 seconds, this hold timer should switch to 20 seconds. And we get into our labs, we're going to see if that change actually happens. We'll check the interface to see if the interface made that change and do a Wireshark capture. Another thing that has to match between interfaces is the area ID. And again, another great example of why we use that interface language or vernacular. Because this R1 right here could have another interface connected to R3, and they could be running OSPF as area 51, and this could be area 0. So this router is participating in two different OSPF routing areas, but the interfaces that are sending the hellos have to match. So if this is sending area 51, then this interface also has to be area 51 for them to become OSPF neighbors on the actual interfaces. And then the MTU size of the interfaces or that link also have to match. So again, let's just clean this up real quick. Let's say R1 has another connection here to R3. And let's say we configure this link as 1400 MTU size. And then these are left at default at 1500. That's good to go. This is going to become neighbors with this router, and this is going to become neighbors with this router. Because at the link level, we're worried about the MTUs matching to form neighborship. Another one that's not said a lot that does matter in the parameters for them to become neighbors, or to really become fully adjacent, I should say, is if we have a network like this, right? And let's say all these routers are connected via a switch. So we have a broadcast Ethernet segment. If this router has the same router ID, and this router has the same router ID, and they all have the same router IDs, we actually are going to have problems. And we'll break that down further along in these videos. Essentially, it comes down to the way broadcast networks work and the DR-BDR relationship and sending LSAs and database descriptions, that you kind of have to have different router IDs in that broadcast network. You're going to have issues. And we'll see that in our lab environment as well. Okay, so once neighbors are formed, and we just learned how we form neighbors, right? Hello packets have to match. The link state databases are going to begin their synchronization process. And what that link state database is again, just imagine we have these networks on R1 /31/24. And once we enable OSPF on this router, these links are going to build what we call a link state database. And that's going to be essentially what it knows about, right? All the networks it knows about. This router and this OSPF router and any other connected OSPF router have to all synchronize their link state databases to become fully converged and at what we call a full state for routes to be placed into the global routing table and begin routing packets. So once neighborship is formed, now we have to build our adjacencies, our actual link state databases within the routers, or our adjacency tables. So during this process, we're going to send what we call database description packets. You're going to see me sometimes give them an acronym of DBD. And in those database description packets, a couple things are going to happen. One, a master/slave relationship is going to form between neighbors. And again, depending on the network type, in a broadcast network, this is going to happen. And the master, which ends up becoming the DR designated router, and the slave, which doesn't have a designation, right? We maybe just call it a druther, right? Is going to share all of its information to that designated router, and the designated router is going to send those LSA requests and updates and acknowledgments out to all its neighbors. And that's how they're going to synchronize their link state database. So once that master-slave relationship between neighbors is formed, again, link state request list and LSA flooding is going to happen. So what this means essentially is that every router, after these database description packets are sent between, a slave is going to have what we call a link state request list saying, okay, I still don't know about this. So it's going to send an LSA request packet out to the master or the designated router. The designated router is going to send an LSA update back. And then that slave router is going to send an LSA acknowledgement back. And it's going to do that until this link state request list is empty. And then it's going to go into that full state, because now the link state databases are synchronized once this request list is empty. And we call this process LSA flooding, because just imagine, maybe 5 to 10 routers all on an Ethernet segment. So imagine all these links are just connected to a switch or some sort of Ethernet relay design, right? Maybe we're in an ISP or data center with all these routers, whatever the case may be. Essentially, that's what's going to happen. LSAs are going to be sent everywhere, right? So we call this process LSA flooding. So once those databases are synchronized and all the LSAs have been flooded within that OSPF network, the link state database is fully populated, and all those routers are going to share that same link state database within an area. And we're going to get into this more when we do the demonstration in the labs, what we mean by within an area, right? Because OSPF can have multi-areas, and it always has that backbone area. We call this full convergence, right? So the network has fully converged when all the link state databases are the same. And within that fully converged network, the actual shortest path algorithm is now going to be executed. And the networks with the lowest cost to a destination, so the best path, right? The best metric, which is the lowest cost. And this is an actual number, right? So like between a cost of 10 and 100, 10 is better. They're going to be placed into the global routing table. And we can see our little example router table here. O for OSPF, the destination network, administrative distance, and then the cost right here. So this route that was placed into the global routing table came from the fully converged link state database of R1 or R2 here. And then once we're in that fully converged state, we don't send any updates, like periodic updates, like let's say RIP would, until there's a change in the topology. So let's say this R1 has the 10.10.20 network, right? And it comes down, that link goes down. So there's a link state change, right? The state of that link came down. Then that's going to trigger updates to its neighbors. Until then, there's just going to be, of course, the hello and hold timers between these routers, making sure that the other side is still alive, but also a 30-minute update as well. And this update's really just going to be hey, is your link state still the same every 30 minutes, okay? And this differs from like distance vector routing protocols that send periodic updates or advertisements every 30 seconds. Okay, and then what is the metric? So the metric or the actual algorithm of the OSPF is pretty simple. The way we described it in the CCNA, right? It's based off a reference bandwidth. So the state of that link, right? So if that link, where that LSA was learned, that network was learned from, is from a gig interface, right? The actual bandwidth of that is going to be 100 megabits, right? And then in the algorithm, there's what we call reference bandwidth. The default's 100. So they're going to do that division here, and that's going to equal a cost of 1, actually. And we're going to get into this as well, because remember, OSPF was made before gig ports were the standard, right? So this reference bandwidth of 100 is what we use to divide our actual bandwidth. We can adjust this to be higher so that we can actually make a different cost value between a gig and fast Ethernet, right? And we'll get into that later with this chart. And then once the network converges, there's no periodic updates except for that 30-minute one I was talking about. LSAs are only sent again if there is a topology change. Okay, so that was just a high-level overview of the entire OSPF operation and how we go from a router that's just sitting there with no dynamic routing, from enabling OSPF, what it does in the entire process. And again, this is done all very quickly, right? It seems like, oh my God, so much, but this is done in seconds, right? Sometimes faster. Now, I will say, like in lab environments, OSPF does take a little longer to come up with a bunch of routers than, like, let's say AirJP or RIP, but that's only because of that LSA flooding, and it's really minimal. It's like maybe a second or two difference, right? But again, that's the entire OSPF operation, right? So now let's get into OSPF network types. I told you there's going to be a bunch of different network types. So I have 5 types up here, but only 4 listed, and I'm going to explain that, right? So we have 4 different network types that OSPF deals with. And again, these network types are based on the link state. So how that link state is operating, right? Is it Ethernet, frame relay, MPLS? Is it a tunnel interface doing DMVPN? Determines how OSPF may operate differently. So a broadcast network type is going to be the default. Then we have a non-broadcast multiple access, which NBMA. We have point-to-point links, and this will be like your dedicated lease line, usually represented like this in documentation, like a serial interface. And then we have point-to-multi-point network types. And then that 5th one we're not really going to talk about is something called virtual links, which essentially is just a band-aid on discontinuous OSPF routing area domains, essentially allowing an area not connected to the backbone area to believe that it is connected and actually become part of that link state database synchronization between the areas. We use a virtual link for that. We're not going to go over that because in CCNA, it's not talked about. It's not on the exam objective. So in our bonus videos, you'll see me configure it. But as far as you passing the certification exam, we don't need to talk about it. Okay, so let's go over the default. So an OSPF network type broadcast, imagine this is like a shared segment, right? So all these routers are connected to an Ethernet switch. So in an OSPF broadcast network, it's the default state. And it's when all the OSPF routers are connected on a shared medium, right? So for this example, just imagine this is one switch. So the OSPF broadcast network has a default hello and hold time of 10 and 40 seconds. Something to note, okay? OSPF broadcast networks will also elect a DR and BDR. So they're going to do that designated router and backup designated router election, all right, during that adjacency table forming, okay? So when you go from the X start, the X exchange states we're going to get into. And in the broadcast network, you're going to have two multicast addresses. One is going to be the designated router multicast address, and one is going to be the all routers multicast address. So one is going to be when traffic is just for the designated router, and one is going to be for any other OSPF router, okay? And just to be sure, because for some reason I'm blanking on it right now, let's make sure those multicast addresses are correct. So actually, let's flip that. Yeah, I'm feeling, right? So this is going to be the all routers multicast address. So all routers are going to receive traffic on this multicast address destination. And this 224.0.0.6 is going to be for the DR, okay? Awesome. And of course, the BDR. So important things to note before I move on. Again, it's just that default hello and hold timers of a broadcast network, and also the DR BDR election. So if someone were to ask you in a tech interview, hey, I want an OSPF connection, but I don't want DR BDR election, what type of network am I going to be? Well, you already know that if you're a broadcast network, you need a DR BDR election. Okay, so you can kind of cross that off the list, right? So now let's go into the non-broadcast multiple access. And I just put an example up here of a DMVPN because that's what I've seen it before, right? An OSPF MBA network will also need to elect the DR and BDR. So non-broadcast multiple access network will also elect the DR and BDR. However, the hello and hold timers are different. So they're going to be 30 seconds. Excuse me, that should be 40 seconds and 120 seconds. So let me just go ahead and fix that right now. The beauty of using Canva. All right. So that's going to be the defaults in an MBMA network. Again, wait, actually, my fault. Yes, it's times 4. So it is 30. Whew, sorry about that. No, that is correct. So the defaults are 30 and 120 seconds, right? And remember, the hello timers are going to be multiplied by 4 to get that hold time, okay? And then in an OSPF MBMA network, it does not use the OSPF multicast addresses to send LSAs. It will actually use a unicast address and requires extra configuration to form neighbors. So what does that mean? That means that they're going to send this command called neighbor, and then you actually put the destination address. So between R1 to R2, right? That could be, let's say R2's network is 10.10.10.5. That's going to be neighbor, right? 10.10.10.5. And that's going to be under the actual interface configuration. Okay, now let's move on. Point to point. So in an OSPF point-to-point network, it's not a multi-access network and therefore does not actually require a DR or BDR election. So in a point-to-point network, you do not need DR or BDR. So essentially, those routers are just going to send LSA updates to each other without the need for a master or slave relationship. Okay. And again, it's not multi access. So that's why it's just two routers here in a point to point connection. You don't need a DR and BDR, right? They're fine with flooding each other with their LSAs and not having that router to be the master of that and control that. And then an OSPF point-to-point network defaults are still going to be 10 and 40 seconds. And then an OSPF point-to-point network will also use the OSPF multicast address to send LSAs. All right. And then we have point-to-multipoint. So point-to-multipoint is also not actually considered a multi-access network. And you can see our example of this MPLS network here. You could say, well, isn't it all access from one router? But when we use something like OSPF, we're actually being segmented at layer 2 or 3, depending on our design, right? So it's not multi-access. It actually would be considered its own link, right, to R1 from R2, from R1 to R3. All right. So an OSPF point-to-point network does not use the OSPF multicast addresses to send LSAs. It will use a unicast address and requires extra configuration to form neighbors. So essentially, what that means is it's going to have that neighbor command as well. So at the actual interface level, so like at gig 00, again, you're going to have sub interfaces for this MPLS connections, but at the actual interface level, you're going to type in that neighbor command again with the destination address. All right, awesome. Okay, so now let's go ahead and take a pause here, and we're going to get into the OSPF rules. So I don't want this video, being an hour long. I like to separate it a little bit. So when we come back, we're going to go over the OSPF rules, and then the tables and the OSPF formation, actually kind of deep dive into hello packets and the actual adjacency building. And then we should, after that, be getting into the configuration. So stay tuned.